Congratulations to all of the students who successfully completed Phase 1 of IA Educational Institute's Spring 2008 Integrated Algebra and Geometry Rocketry Experiment. As you might have noticed, this lesson has a lot to do with vectors, which was a very big and important topic in the Spring 2008 at IA Educational Institute in the Integrated Algebra and Geometry class. A scalar quantity, as this NASA photo says, has only magnitude. A vector quantity has both magnitude and direction. Examples of vectors include displacement, velocity, acceleration, momentum, force, lift, drag, thrust, and weight. All of these are very important in aircraft flight. Vector addition was a very important topic. We spent a lot of time adding vectors, and in our vector addition problems, many of our examples included real-world problems, such as people skiing and people lifting. Vectors have a very important place in analyzing aircraft and spacecraft in any type of flight, be it flight inside the Earth's atmosphere or space flight. Particularly inside of the Earth's atmosphere, you have four forces acting upon an aircraft. This is drag, thrust, lift, and gravity. Keeping this in mind, vectors are acting upon an aircraft at all times. And as you design your rockets, it is highly imperative that you take into account how your rocket will interact with these forces in order to get your optimum levels of performance. One of the things that you particularly have to be considerate about is the force of drag. The force of drag is constantly acting upon an aircraft, and it is the force that is created by air resistance to an aircraft as it obtains motion and as it increases velocity. Cars also have to endure aerodynamic drag, and you may also notice that a lot of your faster cars are sleek in design, such as Corvettes and Ferraris and other sports cars. This is because their designs are resistant to aerodynamic drag, and they are more conducive of airflow. The same applies to airplanes. An airplane's design is very important in determining how it will deal with the air resistance and how much drag will be created by the airplane's ability to go with airflow or provide barriers to airflow. This particular picture gives you an idea of how shapes of different wings or different aircraft parts can increase a drag coefficient. The drag coefficient is a measure of how much drag an aircraft or a car or any kind of vehicle would endure as a result of its motion. Nasha Smith is one of the students that was in one of the groups, and what Nasha found out was that in order to successfully launch a vehicle to overcome the force of gravity, you must have an air pump that is conducive to launch. This is Nasha's rocket that apparently is constructed from a Coke bottle and foam. The foam was used as the wings for the rocket. Nasha was unable to launch her particular rocket because her launcher wasn't able to generate enough power. But once Nasha has developed a launcher that is capable of putting this rocket in the air, she's got to a point where she has other variables that she'll need to deal with. Ayala James, her teammate, was able to get her rocket into the air, but the rocket disintegrated. However, Ayala was able to reach a maximum altitude of 76 feet, which was shortly shy of 1/3 of the goal of 300 feet that was set by this particular activity. Ayala used the Sprite bottle and she used different paper parts to construct the different parts of the rocket. Ayala's launcher was able to generate enough power in order for her to launch it into the air. Michael used paper plates as wings. Whether or not his rocket disintegrated in the air is unknown at the moment, because he wasn't able to present at the time in which his group presented. You might notice that some of the fastest aircraft have a particular design to them. Here is the X-15. The X-15 is currently the second fastest aircraft that was ever constructed, and it is still the fastest manned aircraft that was ever constructed. The X-15 was able to reach a speed of Mach 6, which is 6 times the speed of sound. If you notice, the X-15 is very sleek in its design. The SR-71 is also sleek in its design. The SR-71 has wide wings, but the fuselage is sleek and long, and the airplane is designed so that the airflow would flow over the airplane with ease. The SR-71 is currently the world's fastest jet airplane. The X-15, which was able to reach a faster speed of Mach 6 than the SR-71's Mach 3, was a rocket plane. The SR-71 is a jet-powered plane and was unable to reach the speed that rocket planes have flown. This is the MiG-21. The MiG-21 is a Russian-designed fighter plane. The MiG-21 is a supersonic aircraft, but it is also highly maneuverable because it has a delta-shaped wing that not only allows it to gain a high speed, but it allows it to maintain a steady airflow over the aircraft that it can manipulate into movement. The F-14 Tomcat was for a long time the United States Navy's primary aircraft carrier-based fighter. The F-14 was a significant airplane because it had a sleek design where its wings were swept back, but the wings could sweep forward during low speeds. This allowed the F-14 to both fly at slow attack speeds and at fast attack speeds. The Space Shuttle is a hypersonic aircraft. It goes into space like a rocket, orbits like a spacecraft, and it returns to the Earth as an aircraft. It's somewhat delta wing shaped as well. When the Space Shuttle returns to Earth, it returns to the Earth as a glider. It's no longer powered because all of its rocket fuel was used to re-enter the atmosphere, so it glides back to the Earth. Its design allows it both to slow down from its hypersonic speed once it enters the Earth, and it allows it to stay aloft for certain periods of time until it is able to reach its landing destination, which is usually Edwards Air Force Base in California. So the lessons from phase 1 are as follows. Force vectors are acting upon your rocket at all times. Secondly, in order for your rocket to have enough power to perform its task, you will have to have an air pump suitable for the size bottle that you choose. 3. You must choose the right mixture of water and air pressure in order to get your optimum flight performance. Number 4. Aerodynamic drag can cause your rocket to disintegrate once your rocket reaches a rate of acceleration where the air resistance is too much for the structure of the rocket to handle. You must design your rocket so that it can handle the speed that you intend for it. Thank you very much.